with the formula sheet that I came up with, it's a little more organized than other ones that I've had before. I asked her if y'all were supposed to recognize particular op amps, and she told me inverting and non-inverting op amps. And so I have those right here. Keep in mind that whether you have the plus on top or the minus on top is just, however that person drew it. It's not a standard, so you do need to pay attention as to which one is positive and which one is negative. And the op amps that fit into these categories don't always look exactly like this, and we'll see that in the examples that we do. But primarily for the non-inverting amplifier, what you're going to be looking for is that you have the feedback going back in to the negative. So it's coming from the output, and then the feedback's going back into the negative, and you have those two resistors there at the output. So that's what you would see for the non-inverting amplifier. You might have other stuff in there as well. For the inverting amplifier, you also have the feedback going back into the negative, but in this case, you have a resistor between the V out and the negative, and so that would be what you'd be looking for there. So, and we'll see a couple examples of those. And then the op amp formulas that you should know, the most important ones is that, and if you don't recognize it, you can always work op amp problems just by using these rules, that VP has to equal VN. That's, if it's an ideal op amp, that's the way it is. And IP has to equal IN, has to equal 0. And if you use those, you can solve your op amp problems. Now, this first one here gives the linear range of an op amp. And I wasn't going to do this, and then I saw that it just happened to show up on one of the problems that I did. I don't know if it's something y'all are required to know, but I put it on there. Do y'all get to make your own formula sheet?
Yeah.
Okay, you might as well put it on there, and when I do it, you'll see how it works. It's not the major part of the problem. And then for capacitors, you have the volts. Well, the main thing for a capacitor is that I of t equals C dV dt. So that's the fundamental equation for a capacitor. And then from that, if you integrate, then you can get the voltage. And power always equals VI, V times I. So you take your function for your voltage times your function for your current, and multiply those. And since the current is C dV dt, then if you replaced I with C dV dt, you would get this expression for the power as well. Capacitors act opposite to resistors in terms of combining them. When they're in series, you do product over sum. That's if you have two of them. If you have more than two, then I recommend doing them a pair at a time, or then if you have to do 1 over C1 plus 1 over C2 plus 1 over C3. And when they're in parallel, you just add them together. The energy stored in a capacitor is 1/2 CV squared. And then, important in solving RC circuits, well, in solving any kinds of problems where you have a circuit with a capacitor, under DC conditions, capacitors act as open circuits. And very important, capacitors cannot change voltage instantaneously. They can change current instantaneously, they cannot change voltage instantaneously. Inductors, you have that it's kind of the opposite of a capacitor. For a capacitor, you have I equals C dV dt. For an inductor, you have V equals L di dt. And you also can find the current from by integrating that. Power, again, is V times I. If you have the voltage and you have the current, you can multiply those together. Inductors add just like resistors. So if they're in series, you just add them together. If they're in parallel, you do product over sum. And the energy is 1/2 Li squared. And under DC conditions, inductors act as short circuits. And inductors can, that's so wrong. Oh no. Oh no, and I was so proud of it, and it's sitting up there with the wrong thing. They cannot change current instantaneously. Okay, I'm going to go fix that right away. Okay, now these formulas for RC and LC circuits, they will really help you out a whole lot. You can solve these circuits using first order differential equations, but if you can get them down to where you can identify what the equivalent resistance is and or the equivalent inductance and capacitance, then you can just use, and you have to find for a capacitor, the voltage at infinity, the voltage at 0, and for an inductor, the current at infinity and the current at 0. And if you can find those and the time constant, then you can just use this to find a formula. And then if you need to find the other one, you can use the relationships up here to find the one that you don't have. To find R equivalent for the time constant for either RL or RC circuits, when you're looking for that R equivalent, you're going to find R Thevenin. And what you do is you take your circuit during the transient state and you short out the voltage sources and you make the current sources open circuits. And then once you've done that, you look at where the capacitor or the inductor is and you find the resistance as seen by that element. So that's your formula sheet.